Welcome everyone. I'm Dr. Larry Sterna. In previous videos, I talked about the electric field. In this video, I'm going to talk about what happens to insulators and conductors when you place them in an electric field. Let's begin. Let's start by considering what happens when you put a non-polar insulator in an electric field. This could be something as simple as helium gas, just neutral atoms of helium in an electric field. The electric force, which is a vector, is given by the charge Q times the electric field, which is also a vector. Therefore, the force on each positive nucleus will be in the direction of the electric field. But the force on the electrons, which are negative, will be in a direction opposite to the electric field. Remember, the nuclei are much more massive than the electrons. Therefore, the predominant effect of the electric field will be to distort the electron clouds. So let's consider what happens when you apply an electric field to a sample of helium gas. You see, you have induced a dipole in each atom of helium. The nuclei have not appreciably moved, but the electrons, which are much lighter, have moved opposite to the direction of the field. So you've induced a dipole in each of these neutral atoms. Helium is an example of what you would expect to happen to any nonpolar material, whether it's made up of atoms or molecules, when you place the material in an electric field. Let's consider what happens when a polar insulator is placed in an electric field. How do you obtain a polar insulator? Well, it's very common when atoms combine to form molecules. They share the electrons. But some of the atoms draw the electrons more strongly to themselves than other atoms. An example, if you combine a hydrogen atom with a chlorine atom to get hydrogen chloride, the electrons are drawn more strongly to the chlorine than to the hydrogen. What happens is one end of the molecule becomes a little more negative, the other end of the molecule is a little more positive. That's indicated by these objects here. The Greek delta, meaning a partial positive charge, delta plus, and delta minus, meaning a partial negative charge. So these molecules are said to have a dipole moment. Very common. And so you have one end of the molecule is partially positive, the other end partially negative. What happens when you apply an electric field or you place this material in an electric field? Well, the force on the positive charges will be in the direction of the electric field, and on the negative will be opposite to the electric field. Previously, I said, well, only the electrons will respond because they're very light compared to the nuclei. But in this case, the partial positive and partial negative apply to parts of a molecule. Therefore, both charges have mass associated with them, and both will respond in a similar fashion. The positive will go in the direction of the field, the negative in the direction opposite the field. So what will happen is the electric field will orient the dipoles. It will not move them to the left or the right because the molecule has an equal amount of positive and negative, but it will rotate them. So they line up with the negative ends going away from the direction of the field, the positive ends going in the direction of the electric field. This phenomenon of using electric fields to orient dipoles has a very important application in what is called the liquid crystal display. Liquid crystals are long polar molecules that can be oriented rapidly in electric fields. And they're used to control the passage of light and create the displays for computers, for televisions, for smartphones. What happens when you apply an electric field to a conductor? Let's first consider the structure of a typical metal. For example, copper. You start with copper atoms. Each atom is neutral. The atoms are combined to form the metal. When the atoms are combined, each atom of the metal typically contributes 1 electron to the metal, and you're left with a positive ion. The lattice structure of the metal is composed of these positive metal ions. The electrons are free to move around the metal. In fact, they behave almost like a gas that's free to move around. What happens when you apply an electric field to this metal? Well, we know the rule. The force on the positive charges will be in the direction of the field. The force on the negative charges will be opposite the direction of the field. The positive metal ions are held together in the lattice of the metal. They're not going to move. However, the electrons can move through metal. When we say electrons, we mean the electrons that were donated to the metal by each metal atom. These are called the conduction electrons. They will move opposite to the direction of the field. If you allow electrons to enter one end of the conductor and leave the other end of the conductor, you'll have a continuous flow of electrons through the conductor. And this is what you have in an electrical circuit. What happens if you place a conductor, a piece of metal, in an electric field, and electrons are not free to enter one end and leave the other end of the conductor? Let's consider what will happen. Suppose we place positive charges on the left, negative charges on the right. This is outside the conductor. Electric field lines will proceed from the positive charges through the metal toward the negative charges. We have an electric field going through the metal from left to right. What will happen? Remember, the positive metal ions are not free to move, but the electrons will move opposite direction of the field. Therefore, electrons will move from the right side of the conductor to the left side of the conductor. They will leave behind on the right side the positive metal ions. And so we have a condition where we have negative charges on one side of the conductor, positive on the other side. Note that these charges are at the surface of the conductor. These positive and negative charges within the conductor will create an electric field. The electric field will proceed from the positive charges, these are the metal ions inside the conductor, toward the electrons that have moved to the other side of the conductor. What will happen? Electrons will continue to move from the right side of the conductor to the left until the two electric fields cancel one another. There's so much charge from the electrons on the left, the positive ions on the right, that the electric field from those charges cancels the electric field we have applied from the outside. Electric field vanishes inside the conductor. If the electric field is zero, remember force is equal to Q times E. The force on the charges is also zero. When the forces sum to zero, this is the condition of equilibrium. We say, therefore, when a conductor is at equilibrium, that the electric field inside the conductor vanishes. Very important principle. In this video, I discussed what happens to insulators and conductors when they're placed in an electric field. These are important phenomena that will appear in later videos. But for now, you may be wondering, how do we create these electric fields? We'll look at that subject in the next video, where I discuss the electric potential. See you there.